welcome back for another physics video. We've been talking about work and energy, and we are going to continue that conversation talking about potential energy. So what is potential energy? Potential energy is energy that is stored in a system, and it is available to do work because of its relationship to other elements of the system. So it is energy that is stored to do work. And there are several different types. There's mechanical, which is mostly what we're going to talk about. There is electric, chemical, nuclear, and others. But we're really only going to concern ourselves with mechanical energy. And mechanical energy can be broken down into two major types: gravitational and elastic. Potential energy is usually given the symbol U, but in this class we are going to use the symbol PE. So anytime you see capital P, capital E, that is potential energy. And then the type of potential energy will be indicated by a subscript after. So potential energy gravitational will have a G here. Elastic will have an E, and so on and so forth. And potential energy, like any other energy, is measured in joules. So an object can have potential energy by virtue of its surroundings. So an object does not have potential energy just all by itself. You have to take into account its surroundings, or what we call the system that it's in. Some examples of potential energy are a wound up spring. So if we have a spring and it's wound very, very tight, and there's an object here, once you let go of that object, the stored energy in that spring can then do work on the object to move it some distance. Another example that's kind of the opposite is a stretched elastic band. If you have a really, really stretched out rubber band and it's being pulled on either end by a hook or something, if you let one of those hooks go, the rubber band will then contract in on itself because there was energy stored in that band that can now do work once it's released. And finally, another example is an object at some height above the ground. So if we look at a skydiver falling through the air and the ground is down here, they've jumped out of the plane. The only way that they can go is down because of gravity. So they have energy stored inside themselves because of their position relative to the ground. So gravitational potential energy is stored energy due to raising a mass some height above a certain point. And we get our equation for gravitational potential energy by looking at the work done. So the work done on an object is the force times the distance times the cosine of the angle. We already know this from 2 videos ago. But we can actually use this equation to solve for the potential energy in an object due to its position above the ground. The cosine of 0, if you plug that into your calculator, is going to go to 1. So that makes our job easy. That means now our equation has gone to work equals force times distance. And if you think about it, if you are lifting some object off the ground, the other force you have to overcome here is gravity. Gravity is pulling down on this object. And in order to lift it up, you have to pull upward, opposite gravity, just as much, if not more, than gravity is pulling it down. If you didn't push up as much as gravity pulls down, the gravity arrow would be much longer than your force arrow, and it would fall down. So, what this tells us is that we know the force here must be equal to the weight of the object. It must be equal to the force with which gravity pulls it down. Otherwise, you're not going to be able to lift this object up. And if you remember, the weight of an object can be calculated by taking its mass and multiplying by 9.8 meters per second squared, the acceleration due to gravity. That is pretty much what has happened over here. This is our force, mass times the acceleration due to gravity, and h is just another way to say distance. This object is only being lifted straight up. It's not moving over side to side. So we can call the distance it travels its height. So that gives us our equation for gravitational potential energy. The stored energy that is available to do work in an object that's lifted up above some reference point is equal to its mass times the height from the reference point times the acceleration due to gravity, which is 9.8 meters per second squared. And we got that equation just from looking at our work equation that we learned in 2 videos ago. So there are some really important points about potential energy. This potential energy can become kinetic energy if the object is dropped. The example of the skydiver, if they are taken 3,000 feet above the ground, they have 3,000 feet of height difference to store up that gravitational potential energy. When they jump out of the plane, the height between them and the ground decreases. So the amount of gravitational potential energy they have becomes less and less as they fall. But that doesn't mean they lose energy. They're just converting that energy into a different kind. And if you think about it, when somebody jumps out of a plane, they're going to speed up. They're going to continue to accelerate because gravity is always pulling down on them, and it's always applying an acceleration of 9.8 meters per second squared. It turns out that at a certain point, that person will stop accelerating, but we're just going to assume that they keep speeding up and speeding up. So their potential energy becomes kinetic energy as their motion increases. And the other important point is that potential energy is a property of a system as a whole and not just of the object. If we were to look just at the skydiver and not worry about where the ground was, we really couldn't tell if they had any gravitational potential energy or not because we wouldn't have a height. We wouldn't have a reference from which to measure the height of that person. In order to calculate and talk about the gravitational potential energy that skydiver has, we really have to look at them in reference to the ground. So if potential energy is equal to mgh, mass times gravity times height, where do we measure h from? It turns out it doesn't matter as long as we are consistent. So in this problem, I can measure the change in potential energy from the bottom step to the top step. I can measure how much gravitational potential energy that slinky has at the top step. But if I do the problem a second time and I change my initial reference frame to the middle of the stairs, the amount of gravitational potential energy here is going to be different. However, if we're looking at changes in gravitational potential energy, the amount that changes from here to here and the amount that changes from here to here are going to be the same as the amount from here all the way down. So when we talk about the amount of gravitational potential energy that an object has, we are really talking about the change it can have. The other kind of potential energy that we're going to talk about is elastic potential energy. And this is where the spring and the elastic from the examples in the beginning come from. Potential energy can also be stored in a spring when it is compressed. And the figure below shows the potential energy. So if this is our spring and it's just hanging out, it's not going to do work on anything. But if a hand comes along and squishes the spring so that it is much shorter, there's a bunch of stored energy in that spring now. That is what we call elastic potential energy. And when you let go, when the hand moves, that elastic potential energy can then do work on this ball. It applies a force to move it some distance. It does work on the ball. Work can also be done and elastic potential energy stored in a spring if it is stretched. So there are two ways to store elastic potential energy in a spring. You can compress it, like this one, or you can stretch it, like this one. Either way, there is going to be a force coming from the spring that wants to restore it, wants to bring it back to its happy place. This is its normal resting spot. This is where it wants to be. So the force required to compress or stretch a spring is this. Force of the spring, and we call this a restorative force because it is the force that wants to restore the spring to its happy place. So we have the force is equal to the spring constant times the displacement of the spring. The spring constant tells us how springy the spring is. So the higher the spring constant, the stiffer the spring is going to be, and the harder it will be to move it from its happy place. So a really good example of this is a shock in a car. I don't know if anybody has seen one of those, but they are gigantic, and they are incredibly difficult to displace. They are incredibly difficult to squish or stretch. And that spring is going to have a very, very high spring constant. An example of something with a very low spring constant is a slinky. A slinky is fairly easy to stretch and compress, so that has a very low spring constant. It requires very little force to displace the spring from its happy place. So like I said, the spring constant is a measure of how loose or stiff a spring is. Springs with high values of K need a lot of force to displacement and displace them, and springs with low values don't need much force. And hopefully you all recognize this formula, F equals Kx. It's called Hooke's law, and you all did a lab on it last week, at least the students in my class did. And this was discovered by Robert Hooke, and it says that the restoring force on a spring, the force to bring it back to its happy place, is equal to the displacement from equilibrium times the spring constant. And this is an important point, displacement from the equilibrium, from its happy place. We don't measure displacement from the end of the spring, where it's touching the table or the wall or whatever. We measure how far it gets stretched from its natural resting spot. And remember, force is measured in newtons, and displacement is measured in meters. So the SI units for the spring constant are newtons per meter. And what that tells you is how many newtons you need of force to displace your spring 1 meter. So it makes sense that a spring with a very high spring constant will need lots of newtons to stretch it 1 meter. It needs a lot of force. The spring constant is always a positive number. The reason there's a negative sign in this equation is because the restoring force is going to be in the opposite direction of the displacement. So if we have a spring and it's in its happy place, and you crumple it up, you have displaced it this way. So in order to get back to its happy place, the force needs to be this way. And the opposite is true if you stretch the spring out. If you stretch it out, you have displaced it in this direction, and the force required to restore it to its happy place must be in that direction. So the negative here is just telling you the restorative force acts opposite the direction of displacement. The spring constant is usually determined by doing a Hooke's law experiment, and you should be familiar with this since we did it last week. Masses are hung on a spring, and the displacement of each mass is measured. So the mass will go up here on this spring, and how much it displaces gives you the displacement. Then a plot is made of force and displacement. And remember, the force here, the force that the mass pulls down on the spring with, is going to be its weight. And weight is mass times acceleration due to gravity, 9.8. And the slope of this line gives us the value of the spring constant. So if we were to graph the force on a spring this way and the displacement this way, the slope of this line right here is the spring constant. And this is a very important point because when we talk about elastic potential energy, the spring constant of the spring we're concerned about is a very important factor. So it turns out that the energy in a spring is not a linear function, which means it doesn't change in a linear way along a straight line path like this. The force increases as the spring is stretched or compressed further. So the more you stretch or compress it, the larger the force will be. And we find that the potential energy of a compressed or stretched spring follows this equation. So elastic potential energy, PE little e, is equal to 1/2 times the spring constant times the square of the displacement. And this is one of those equations where you have to make sure you square the displacement only. You do not plug in 1/2 kx and then square the whole thing. You only square x. And it turns out, a nifty little math thing that is actually quite important, but we're not really going to get into, is that if you plot the force on a spring here against its displacement here, and you get Hooke's law here, the area under the curve is elastic potential energy. So the more force you apply, the farther the displacement, and the greater the elastic potential energy will be in a non-linear way. So now it's your turn to try some problems. Batman, the Dark Knight. I'm wondering how much potential energy this 75-kilogram Batman has when he jumps off the top of Gotham Tower, which is 400 meters high. How much potential energy does he have? And how fast is he going when he reaches the ground? And I'm going to give you a hint here. Use kinematic equations. So draw a picture, make a chart of what you know and what you don't know.